So for today we are going to start motion. Let's go. So before we talk about motion, we got to do a little bit about frames of reference. A frame of reference is a basis from which motion is measured. All right. So this should make sense because if you're moving and the other thing is moving, well, it might cancel out so it looks like they're not moving. So you need a frame of reference that you're using when you're describing motion. If I say you're going 100 miles an hour, well, in reference to what? If you're going in reference to the ground, that's really quick. If you're going in reference to the sun, that's not really that quick. So it's all about your frame of reference. Now, most of the time, it's going to be usually the ground. Your ground is going to be your frame of reference more often than not. But it doesn't have to be, and there's no universal frame of reference because it all depends on where you're standing. Don't mean to get philosophical here, but they break down into two categories. Category 1 is inertial. Category 2 is non-inertial. All right, those are the two types of frames of reference. Now, we'll talk about inertial first. Now, in inertial, physics is normal. Now, as normal as it ever is, right? But things work the way you'd expect. Now, how you can be in an inertial frame of reference is you have a constant velocity. Okay? So if you have a constant velocity, you're in an inertial frame of reference, and physics is going to be normal. Now, your velocity could be 0. All right? That's fine, as long as it's not changing. Now, we'll talk about velocity more in a little while, so don't worry too much about that word yet, but that's the rule. Now, a non-inertial frame of reference means that there will be a non-inertial will have an external force. Okay, so one example of this is if you've ever been on the turning platforms, like the merry-go-rounds or whatever, it feels like you're getting pushed off. Now that's that external force because it's a non-inertial frame of reference. Now, this means that it is accelerating. That's how you can have a non-inertial frame of reference. It is accelerating. I'm going to say or turning. All right, when you turn the car and you feel yourself getting pushed up against the side window, that's because it's a non-inertial frame of reference. Now, looking at these 4 cars here, some of these have frames of reference, some of these do not. Let's see if you can tell. Looking at this first one is somebody that tried to park and did a terrible job at that. Or they think they're very special, or maybe both, but not in a good way. So this car right here is parked, or at least it was tried to be parked, and so it's going to have an inertial frame of reference because it has a constant velocity. This car right here is accelerating. It's going to be going fast, gotta go fast, so it's going to have a non-inertial frame of reference. This car here is the cruise control at 60 because it doesn't speed, so that's going to be inertial. This car here is a non-inertial because it is turning. If you sat down in this car, you would feel like you're still, just like this car. Those cars would feel stationary if you closed your eyes and it were really smooth. These cars would not feel stationary. These cars you would feel pushed even though you were sitting still. All right, now 2 big words here that we're going to throw around for a while is distance and displacement. Okay, so we're going to start with distance. Distance is how far you travel. That's it. So it's how far you go. All right. We're going to compare that to displacement, whereas displacement is how far you are from start. Okay, so how far you travel and how far you are from start. Now there's some differences in there because if you loop back, your displacement will decrease, right? Now that means, because we'll be working on a coordinate system, right? So if you go the wrong way, that this one can be negative. Right? You can have a negative displacement. All right? Because you could be going the wrong way. Now the negative means it has a direction. So this has a direction. Because it tells you how far you are from start in which way. Whereas distance, going back over here now, cannot be negative. So this must be positive. All right, it must be positive because it's just how much mileage is on your feet. If you go backwards, you're still putting miles on your feet. Okay. Now, let's look at displacement again. We know it has to have a direction, and it has a how far, a how much. So that means it's got a magnitude, which means this number is going to be a vector. Yes. Whoop, vector. So, because it's got a direction and a magnitude, it's a vector. There's two parts to it. Distance is not like that. Distance is just a magnitude. Do you know what that means? It is a scalar. Okay, so those are your two types of numbers. You're going to have a lot of vectors and you're going to have a lot of scalars in your class here. A scalar is just a number. Like, how heavy are you? You're 20 pounds. So that's just a number. It doesn't have anything to do with direction. Whereas displacement is a vector. So how far, where are you? You're 20 feet that way. Okay? So we're going to talk about their brothers now. Speed and velocity. Okay, so let's talk about speed first. Okay, so speed is equal to distance over time. Okay, so T stands for time. Let's jump to velocity. Let's get a definition down. Velocity is equal to displacement over time. All right, same idea here. Now, anything that uses other values, like speed uses distance, for example, that's going to carry all the baggage forward. So, for now, since distance was a scalar and time is a scalar, this is just still going to be a scalar value here. And that means that speed will always be positive. And it's just a number, right? Forward or backwards, doesn't care. Now, velocity deals with displacement. And since this is a vector, that means velocity will also be a vector. Okay? Since it's a vector, it's going to have direction. So if you're talking about how fast you're going, you have to be careful if it's speed or velocity. Usually it's not going to matter, okay? But we're laying down these words and we're going to use them all year and you're going to get a lot better at telling the difference here. Now, the units for these are going to be in meters per second because distance is in meters and time is going to be in seconds. Distance for this one is going to be the same thing because displacement is also in meters and it's still time, so it's not going to change at all. Ta-da! So we're going to do a little bit of practice with this. We're going to figure out the distance, displacement, speed, and velocity of you when you walked around the block. Well, most of the way around the block. You walked around 3/4 of it. It took you 5 seconds to go 6 up, 8 over, and 6 down again. So let's pause the video and see if you can do it. Let's find out. For distance, how much distance did you cover? You went 6 up, 8 over and another 6 down. 6 and 6 is 12 plus 8 is 20 meters. Nice. What's your displacement? Well, this is how far your displacement is. So your displacement is going to be 8 meters. But did you put a direction? I hope so. You can say right. You can say east. Whatever. They're going to specify when it matters, okay? So speed, if we're talking about speed, we know that the distance is 20 divided by the time it took, which is 5. So 20 over 5 is 4.0 meters per second. What about your velocity? You have 8 divided by 5, which is going to be 1.6 meters per second. And you need a direction to it. We'll go east. Ta-da! So that's that. Let's do one more. See if you can figure this out. Oh, so we want the distance, we want the displacement, we want the speed, and we want the velocity. Pause the video, see if you can figure it out. Oh, I didn't think it'd take you that long. All right, let's see. So for distance, boom, boom, we covered 31 meters. Ta-da. Right? Remember, you don't use the 0 for sig figs because you're adding it, and this doesn't have a decimal point or number after it. Ooh, for displacement, what's your displacement? Your displacement is this value. What's this value going to be? Well, do you like your math here? 7 squared plus 24 squared is equal to c squared. Bada bing, bada boom. You're going to get 25 meters. We can say northeast. Does that sound fair enough? Okay, so now for speed. Speed is distance over time. Distance is 31 over 10. So we're going to have 3.1 meters per second. And velocity, we're going to have 25 divided by 10, which is equal to 2.5 meters per second. Northeast. Don't forget those. Cool. How you feeling with that? Well, you'll have to talk louder because I can't hear you through the internet. Well, we got one more thing. Now, each of these speeds and velocities can also have an instantaneous and an average component to there. So let's just think about velocity for now. So this instantaneous is going to be the velocity or speed at an instant. Now we could say instant or like a point. Does that help? So if we were graphing this kind of thing, if here's your velocity, here's your time, your speed goes like this, whatever. This right here, you'd have a tangent line. This is your instantaneous speed at that point. That's the slope right there, right? Your instantaneous. That's how fast you're going at that instant. Now your average speed is going to be over an interval. Okay, so if we're talking same thing, here's your velocity, here's your time, there's your speed. If I take this guy and I figure out the slopes, oh, whoops. Well, that shouldn't be velocity, that should be distance or displacement, doesn't matter. My bad. We're going to talk way more about this next week, so don't worry too much. But it's spread over this interval. So if I averaged all of these instances together, that's fine. And then I'd get that average, okay? So this is like a tangent if you're familiar with your math terms. And this is like a secant. Ta-da. All right. So all you need to keep track from this is average means over the interval, and instantaneous is for that particular point. But they don't have to necessarily be equal to each other, okay? You could have an instantaneous speed of very high, but you averaged a very low. If you were walking, but then you thought someone was chasing you, so you sped up, but once you turned the corner, they were gone, so you were okay. All right, that's it. We'll see you later.